Hello students, welcome back to the class. In the last class, already we studied about the Lorentz transformation equation. So on the basis of Lorentz transformation equation, in the today's class, we are going to derive Lorentz Fitzgerald length contraction. So for this, we want two frame of references, one is S and another one is S dash. So this is the S frame and this is the S dash frame. Whatever the S frame is there, it is at rest position and S dash frame is moving with a certain velocity, that is equal to what? Phi along the positive direction of the x axis. Now something event we are taking at the S dash frame, and that event is nothing but the rod we are taking. So this is the rod what we are taking in a S dash frame. So as the S dash frame is moving means the rod which is there in that frame, it is also moving with the same velocity of the S dash. That's what the thing. So whatever the rod is there, this is having certain length. So what is happening here? There are two observers are there. One is on the S frame and another one is in the S dash frame. The observer who is there on the S frame, he is at rest position with respect to S, because this is also at a rest position. But at the same time, the observer who is there in the S dash frame, he is moving with S dash, isn't it? So for according to him, both the observers are observing or they are calculating the length of the rod. The first observer is also calculating the length of this rod and the second observer is also calculating the length of the same rod. Then when they are calculating, there will be changes is happening, the length of the rod. Actually the length of the rod is L, but when the frame of reference is moving, so while moving, if he did the calculation of that length, then it will be what? Something different he is getting. So now in the today's class, we are going to find what will be the changes of that length of contraction. So how the length, whether it is increases or whether it is decreases or it will be same. So for these questions, we will get answer from the today's class. So let's go into the matter. Consider S and S dash frame. S frame is at a rest position and S dash frame is moving with a velocity phi, and a rod is there in a S dash frame. Both the observers are observing the rod and they are calculating the length. So when we want to calculate the length, the coordinates we should get. This is the first end and this is the last end. So the coordinates of these two ends are nothing but, so let I am taking x1 and x2. See, this is the x1. The first end coordinate is x1 and the last end coordinate is x2. So I am taking, let x1 and x2 be the coordinates. So these are nothing but the what? Coordinates. With respect to what? With respect to S frame. So from the S frame, when you are calculating, the coordinates becomes what? X1 and x2. So at the same time, from the S dash frame, if you find these two coordinates, it becomes what? X1 dash and x2 dash. So I will write x1 dash and x2 dash be the coordinates only, the coordinates of the rod only, but with respect to which frame? With respect to S dash frame. So this is what the thing. So from the S frame, when we observe the coordinates of these two, we are getting x1 and x2. From the S dash, when we are observing the coordinates, it become x1 dash and x2 dash. That's what the thing. So now I will take the Lorentz transformation equation here, because when one frame is at rest and another frame is moving, then what will be the changes of that size of the object or the event we calculated by the what? Lorentz transformation equation, and on that basis we got the first Lorentz transformation equation, which is equal to x dash is equal to x minus phi t divided by square root of 1 minus phi square divided by c square, where x dash is the coordinate of that point with respect to S dash frame, x is the coordinate of the point with respect to S frame, and phi is the velocity with which the S dash frame is moving, and t will be the time at which you are doing this calculation, and last one is the c. So c is nothing but the velocity of the light, as we know already. So same Lorentz transformation equation we are applying to S frame and S dash frame, and now we are getting 2 points here. See, in terms of x1 dash, so if you get this equation and convert the same equation in terms of x2 dash also, so we will get the 2 equation. So I am writing those 2 equation. So first I will write x1 dash equation. So x dash is equal to x minus vt. So x1 dash is equal to what? x1 minus v into t1, isn't it? So x1 minus v into t1 divided by, this will be same because it is moving with the v velocity only, that is the square root of 1 minus v square by c square. Now the same equation if you write in terms of x2 dash, so how we are getting? We are getting x2 dash is equal to x2 minus v into t2 divided by square root of 1 minus v square by c square. So in terms of the Lorentz transformation equation, we got x1 dash and x2 dash. So both equations we got. Now already what I said is, when we are observing, when they are calculating the length with respect to s and with respect to s dash, how they are getting the value. So already we know the coordinates, isn't it? So from these 2 coordinates we should find the length. So that is nothing but the difference of these 2 coordinates, the x2 minus x1. If you you will get the length. At the same time, x2 dash minus x1 dash, if you know, you will get the length, but with respect to the different frame of reference. So now I am writing the equation, that is the length of the rod when calculated from the S frame, how we are getting that, isn't it? So can we write the length as observed from the S frame is equal to x2 minus x1. So are you agree? This is the x2 value and this is the x1 value. So if you do these 2 subtraction, are you getting the length here? This is the length of the rod with respect to what? S frame. And the same way, if you calculate it from the S dash frame, so different length you are getting, that's what I will write it as L0. So L0 is equal to, so now you can tell easily, this is equal to x2 dash minus x1 dash. That's what the thing. So this is the length with respect to S frame when calculated, and this is the length when calculated from the S dash frame, the length of the rod. So now as we are having L0 is equal to x2 dash minus x1 dash. So already we know these 2 values. X2 dash value also we know. At the same time x1 dash value also know. So now I will substitute in the equation. So what I would have get, that is L0 is equal to, what is the x2 dash value? That is x2 minus v2 divided by square root of 1 minus v square by c square. So I will put that one. That is x2 minus vt2 divided by square root of 1 minus v square by c square minus what? x1 dash. So what is the x1 dash? This is the value of the x1 dash. That is minus x1 minus vt1 divided by square root of 1 minus v square by c square. So just I substituted the length as observed from S dash frame, x2 dash minus x1 dash. Already we know the x2 dash value and x1 dash value. So I substituted in the main equation. So we got this equation. Now this is equal to, see, if you observe these 2 terms, the LCM is same in both the terms, isn't it? So same LCM means divided by same quantity we are getting, that is the square root of 1 minus v square by c square, isn't it? And the numerator parts we are getting that x2 minus vt2 minus of x1, and minus minus becomes plus vt1. So we got in the numerator part. So this is equal to, so I will write x2 and this minus x1 first term. So that is x2 minus x1 in the first term minus vt2 plus vt1 is there. So out of these 2 I am taking v as a common, and not v, minus v I will take a common. So if you take, what will be remaining? Yeah, t2 minus T1 divided by square root of 1 minus V square by C square, isn't it? And now, as already I said, these x1 and x2 are the coordinates of the rod with respect to S frame. And if you do that subtraction, that is x2 minus x1, if you are making, what you are getting? The length of the rod, isn't it? That is the value of the L. So instead of x2 minus x1, you can write it as what? L. Minus, see, here we are having the time T1 and T2. So T1 is the time as observed from S frame and T2 is the time as observed from S dash frame. But here what is happening? Both the frame of references are calculating the length of the rod at the same time. At the same time, they are going to calculate the length of the rod. So if it is the case, then whether the T2 and T1 value will be same. So if T1 and T2 value, if it is same, then what we will get? The subtraction, which is equal to 0 we are getting. So V into 0 we are getting, because T2, here you can write, because T2 is equal to T1, so which is equal to T. Same time we are going to observe both the frame of references are observing the length at the same time, so it will be same. So divided by what is remaining? Square root of 1 minus V square by C square. This is what L naught is equal to we got. So now we can write L naught is equal to V into 0 means V 0 only we will get. So L naught is equal to L divided by square root of 1 minus V square by C square. Or if you transfer the term, this denominator term to the LHS side, then L is equal to what you will get? Yeah, you are getting L naught into square root of 1 minus V square by C square. So this is what I want to derive. So this is the Lorentz Fitzgerald length contraction formula. That is L is equal to L naught into square root of 1 minus V square by C square. So as I said, L is the length of the rod with respect to S frame. L naught is the length of the rod with respect to S dash frame. V is the velocity with which the S dash frame is moving and C be the velocity of the light. So if you observe these two things, then something you are getting. That is, see, when in terms of L naught you are calculating, the whatever observed thing is there from the S frame divided by something you are getting. Means L naught value you will get less. See, already with respect to S frame we calculated the length of the rod. We know already. Then with respect to S dash frame, the observer is going to calculate the same length. So if he wants to calculate that length, then he will use this formula, because already we know the L value, isn't it? So when he will do the calculation, something L naught value he will get. Next, reverse order we will calculate. That is, the observer who is there in the S dash frame, already he calculated the length of the rod. Already we know the L naught value. Then with respect to the observer in S frame, if he calculated, then what formula we will use? Yeah, we will use the second formula. So you can, by the common sense, you will get the point that, see, as it is divided, you will get less value of the L naught. But as it is multiplying, means you will get more value of the L. That meaning is, that conclusion is, the length of the rod will appear to be shorter for the observer who is already moving. See, the observer who is there in the S dash frame, he is under the motion. So if he observes the same thing, according to him, the length appears to be shorter than the original value. At the same time, the observer who is there in the S frame, if he observes or if he calculated the length, then it will be more than the S dash frame. Okay. See, actually, in day-to-day life, we will have this application. When aeroplane will be flying in the sky, so as you are on the surface of the earth, so if you see that aeroplane, then you will come to know that the size become compressed there, the size become decreased, isn't it? So that's what I want to say here is, whenever object is under motion, then for the observer who is already moving, according to him the length of the rod or the length of the object becomes shorter than when it is at rest with respect to him. So if the aeroplane is at a rest position, then completely we can get the length. Yeah, if it will be more. But as you are also moving and aeroplane is also moving, and if you observe that length of the aeroplane, of course it will what less you will get than the original value. So that's what is called as what? Lorentz feathered length contraction. So here last word we can write, that is the length of the rod. The length of the rod in motion with respect to the observer. The length of the rod in motion with respect to an observer appears to be what? Yeah, it is appears to be shorter. Appears to be shorter than when it is at rest with respect to him. Then when it is at rest with respect to him. So this is what the thing. This is the Lorentz feathered length contraction. So in examination they may ask the derivation or the problems also, but you should be having the complete knowledge of this one. So whenever they will ask explain or derive Lorentz feathered length contraction, so starting you say, consider S and S dash are two frame of references in which S is at a rest position and S dash is a moving frame of references. Then something event is happening at a S dash frame. So for this, as we are calculating the length, we taken a rod. So the rod is there in a S dash frame. Now what is happening? As it is in a S dash frame, this is moving means the rod is also starts to move with respect to this. So both observers, two observers are there from S and S dash. Both the observers are calculating this length. So when they are going to calculate the length with respect to S observer, the length how it will be looking. At the same time, with respect to S dash, if he calculated the same object of the length, then how it will be looking. So that was the question. So let x1 and x2 be the coordinates with respect to S frame. So from S frame, we calculated the end coordinates. x1 dash and x2 dash be the coordinates of the same object, but with respect to what? S dash frame. So we changed the frame of the reference. So the length of the rod with respect to S frame can be written as L is equal to x2 minus x1. And the length of the rod with respect to S dash frame can be written as L0 is equal to x2 dash minus x1 dash. So these are the two equations we got. Now already we know the Lorentz transformation equation. So what is the Lorentz transformation equation? That is x dash is equal to x minus phi t divided by square root of 1 minus phi square by c square. This is the basic equation for all those things. That is the Lorentz transformation equation. So this equation we are applying to two frame of references. First time S and first time S dash. See, the same equation if you write in terms of x1 dash, so you are getting x1 dash is equal to x1 minus phi t1 divided by square root of 1 minus phi square by c square. The same equation when you will write in terms of x2 dash, so x2 dash it will be x2 minus phi t2 divided by square root of 1 minus phi square by c square. So this is what the thing. Now already we know L and L0 value. So L0 is equal to x2 dash minus x1 dash is there, and already we know these two values. So I had been substituted in the same equation. So when we substituted, we are getting this equation, isn't it? So from this equation, if you solve the things, what you are getting is equal to, as a denominator is same, so same LCM you will get. And what will be in the upper term? Yeah, x2 minus phi t2 minus of x1, minus into minus becomes plus phi t1. Now what happened? Here x2 minus x1, I will make one group here, minus out of these two, phi t2 and phi t1, I taken minus phi outside. So what will be remaining? T2 minus t1 and divided by same quantity we got. And already we know from the first equation, that is L is equal to x2 minus x1. So I substituted the value of the x2 minus x1 is equal to what? L minus phi into, as the length is observed at the same time, so both the values become what? Same, isn't it? At the same time we are going to find the length of the rod. So T2 is equal to what? T1, which is equal to T. So if both are same, when you will do the subtraction, you are getting 0 and divided by square root of 1 minus v square by c square. So if you solve this one, you are getting L naught is equal to L divided by square root of 1 minus v square by c square. Or if you transfer the denominator term to the LHS side, you are getting L is equal to L naught into square root of 1 minus v square by c square. That is, we can say in one word, the length of the rod in motion with respect to the observer appears to be shorter than when it is at rest with respect to him. Means when it is at rest, the length becomes larger, but when it is moving with respect to the observer, it appears to be what? Shorter. And this is known as, you can write, this is known as length Fitzgerald contraction. Okay, so I hope you understood well about this one, and by seeing the video you can write the notes also, isn't it? Okay, so you write the video notes from the video, and in the next class I am going to explain the another thing of the Lorentz transformation equation. Okay, thank you.